And the random walk in the statistical environment, random to the what is that?
That's a doubly stochastic. More drift-free random.
Or divergence-free, random drift-free.
Continuation.
On the showing of
That's not the talk yet, is it?
once you're done, no. Once you're done.
Sorry. I just wanted to not waste time during the talk.
Yeah.
So.
Okay. Alright, welcome everyone. And Professor Bálint is here. As you know, he gave the Ashok Memorial Lecture, the first talk yesterday. Was it yesterday?
Friday.
Last working day.
Today he's going to talk on random walks in doubly stochastic random environments. It's going to be a series of 2 talks.
Yes.
Today and tomorrow.
So thank you very much, and thank you for the invitation. Thank you for giving me the opportunity to give 3 talks here, which one was for the general audience, and this will be more technical about a particular problem, but of course not unrelated to what was done yesterday. Now, before starting to write down mathematical formulas, let me give some examples. These are maps of 3 cities. 3 cities where the streets and avenues or streets go either south-north direction or east-west direction, and the mayor of the city decides about making the streets one-way, essentially. Now, this city has a very democratic leadership, and they say in each block, people can decide whether they want the streets one-way, going clockwise or counterclockwise. That's the choice the people living here make. And people living here make their choice independently, and people living here make their choice independently. These are blocks of houses, and they make the decision. Now, if for example, for this street, it is decided whether on both neighboring blocks they made a decision which are not in contradiction, then they make this street one way. I can't decide about the upper one because I didn't put their boundary conditions. Here, they are in conflict. So then the mayor says, okay, you are in conflict, then we don't make one way this street. Right? Here, they are not in conflict. They make the street one way. Here, let's see what happens here. They are in conflict, so they don't. Here, they are not in conflict, and so on. I could fill it. Let me not fill it because it just takes time. So the rule is the following: in each single block, a decision is made, say independently of one another. Make it one way. Okay, let me finish. That's not a big deal anyway. I have there it's a conflict. Here it's no conflict. Here there is no conflict. Here if there is a conflict. Here there is a conflict.
No conflict.
Here there is no conflict, and I think I filled the inner ones. Right? So this is the inner ones. Okay, but I didn't put, let me put equal, or let me put just some sign to make sure that we have.
No, that's no conflict.
There is there is conflict.
But the next one is no conflict here.
This one.
Yeah.
This goes that way. There should be no conflict, of course. Yes, you are right. It's there. No, something is wrong there.
No, there is conflict.
Sorry?
Conflict.
There is a conflict.
There is a conflict.
There is a conflict.
Okay.
These guys want that way one way. These guys want that way one.
Both are anti-clockwise.
Okay, let's say I think it's okay now. Notice, no, here something is wrong. So they want this way. There is no conflict. Maybe that's what you want.
Okay. Yeah.
And there could be some more complex structures. What you can see that at each single corner, the number of arrows coming in and arrows going on is the same. Now you are a driver in this city, arriving from, this is not Kolkata, and arriving from Calcutta, you drive, and whenever you arrive to a corner, then you have to make a decision. You can go, say, you randomize, because there is no unique rule, namely, with probability, let's say that is the rule that along an arrow, you go with probability 1/2. Along streets which are not one way, you go with probability 1/4, and you don't go against. These add up to 1 everywhere. If you make, it's very easy to see that they add up to 1 everywhere. Now I ask you, are a driver in this street. This is the random environment I created, or the mayor of the city created. And you are totally randomly driving, say, drunken driver who makes the only, okay, not drunken, but doesn't have any final goal, just wants to drive along the streets. And this is the rule I gave you. Now my question is, the city is hugely extended. How far you get in time n? How far you get in time n, in the sense of the central limit theorem? Do you get distance square root of n, or much further out, or much less out? And if any of these, can you say something about the limit? So this is just to check your first intuition. I don't expect, some of you may know the answer. This is well known, I tell you that. This is well known. Okay. I tell you what the answer for this is a random walking random environment. It's clear, right?
Yeah.
It's a random walking random environment. The environment is stationary, in translational, ergodic, right? It's easy to check. That's the number of arrows coming in and coming out add up to the same number. That's by stochasticity. I will make it more formal, or divergence-free character of the flow. If you think about this as flow lines, it's divergence-free. So flow in and flow out is the same, right? And the answer to this question will be that if I call xt the displacement in time t, this will be square root of t. Indeed, I tell you, and you will see. This is not difficult. It's not an easy problem either, but once the techniques are at your hand, it's not difficult. And the central limit theorem. Right? Now this is New York, this is Manhattan. Right? And each avenue and each street is made one way from beginning to the end, but random. So I go to each, the mayor or the leadership of the city decided they had one single coin. They go to each single avenue and decide by a coin whether it make a one-way northbound or one-way southbound, and they make to each single street and decide by tossing a coin whether to let this street be one-way eastbound or one-way westbound. Now here it's even easier to see that at each single corner you will have 2 arrows in, 2 arrows out, right? When you arrive, you can arrive to each corner by driving your car from 2 different directions, and you can leave the corner in 2 different directions, and 2 different directions, but on one-way streets. So the rule is that when you arrive here, you toss a coin, and if it's tails, you go, okay, you choose equally randomly. And at each single corner, you decide by a coin tossing which one to choose of the 2 possibilities. Question is the same, how far you get in time. And if it's square root of time, then is there a central limit theorem there? Any intuition? Okay, I tell you, this one will this is diffusive. This will be super diffusive. And quite robustly super diffusive, namely xt, this is not proved what I'm saying now. It's conjectured, and there are good reasons to conjecture, some scaling argument, sort of physics argument, that xt must be of order t to the 2/3. And actually what we can prove, okay, this blackboard is small. So 1 xt by square root of t converges to a non-degenerate normal. In the second one, this is the expected behavior which we are not able to prove. But we are able to prove, and there is a recently uploaded paper. Actually, we had this result more than about 10 years ago, but we didn't write down with my colleague now, ex-PhD student with Benedek Valko, who is professor at Madison now, and now it's written with Sean Ledger, who also contributed, who is a postdoc in Bristol. And what we can prove in this case is bounds, lower and upper bounds. The lower bounds are the more interesting one, namely take the expected value of xt squared, and we prove, oh, I will be in trouble. So this would be t, that this is t to the 3/2, and this is t to the 5/4, and expected conjectured would be that it is t to the 4/3. No limit theorem, just lower and upper bound. When I write this expectation, I mean expectation with respect to there are two randomness here. Randomness, once the environment is created, is randomly created, and once the environment is there, you have a random walk. So when I just, without any specification, I write this expectation, I mean that I take expectation over all randomnesses. So it's annealed, that's what we call it. It's not a very good name to call it annealed, but that's how it's called in the probability literature. Physically, annealed means slightly different. But anyway, here is the super diffusive lower bound, right? By the way, okay, I speak of 2 dimensions, I will go to the higher dimension in a moment. These are just examples. Now, the mayor of the third city is a person much, much more sophisticated than previous ones. He knows statistical physics.
Just a query, like here the environment is not stationary. Right?
It is stationary. It's stationary and ergodic. At each single line is decided by a coin toss whether to be, which direction to be oriented. With the same, okay, the coin is the same. 1/2, 1/2.
So, but in this case, like, is different. Once we have decided on the orientation and fixed the arrows,
Right.
still this case is different because you are not putting arrows throughout.
No, it's different. These are three, so the results are different. These are three, I just gave you an example.
This is not a divergence.
This is okay, both are divergence-free. Both are. Divergence-free means that if you think about these arrows as flows of the same intensity,
Same arrows going.
then at each single corner, the flow in and flow out is the same. Total flow in and total flow out. Unfortunately, this was drawn in such a way that we don't have, here you can have 2 in and 2 out also. We don't see that, but it is possible. We don't see corners with 2 in and 2 out because my sample is not like that, and we don't see corners with no arrows at all, but it could happen. Here, each single corner is with 2 in and 2 out. Right?
And there is no like, for fluctuations.
Sorry?
There is no conjecture for fluctuations.
That's what I say. The conjecture for the fluctuation of the displacement,
Like
right?
I see. I mean, in the sense of weak convergence, like xt by t to the power.
You mean for the limit theorem?
Limit
Or
theorem.
what the limiting distribution would be? No, there is no. So you have seen that in one dimension, we just quoted 2 of us about my old results, with similar sort of flavor. In one dimension, there is a limiting distribution identified, which is very complicated, but not in the 2-dimensional case. Good. In one dimension for a different. Now the third one is more complex. Looking at each single corner, just empirically, you can see that indeed here we have 2 in and 2 out at each single corner. But it's not that simple as that. This is the so-called, this is the configuration of the so-called 6-vertex model in statistical physics, which means that the constraint is that at each single corner you have 2 in and 2 out. Of course, you can't do it independently because, and take uniformly among these. Uniformly means you have to make it very clear, means take finite boxes, take uniformly finite boxes, take not whatever, so boxes of even length, take all possible configurations, and with equal distribution, let the limit of the box, of the size of the box go to infinity, and the limit exists, and that's the 6-vertex or square ice model is called otherwise. It's a very important and interesting combinatorial object in statistical physics. And now the rule is the same. The rule is the same. You are a driver in this city. You can arrive to each single corner from 2 different directions, and you can leave in 2 different directions, right? And the question is the same. Now here the conjecture, for good reasons, the conjecture is that xt should be of order t, square root of t times, how is it, t to the 1/2 times log t to the 1/4 for some reason, but this is k, what I write here is not proved at all. And we don't have a proof of anything. We are working with Valko on that, but we don't have, what we hope to be able to prove at one point is a lower bound, logarithm, with some logarithmic correction, not like this. But we are far from that. We have, I will, if I have time, I will tell you a continuous space diffusion example, which is closely related to this one, and there we have a proof. So I gave you 3. Okay, before going on, we can of course define this is d, you can define it for d, this is d equals 2, but you can define all models for d equals or greater than 3. So this is d equals 2, but you can define it for d greater than or equal to 3. Take just 3-dimensional grids and do exactly the same. And this one again, so this is the d equals 2, but you are able to define it to d greater than or equal to 3, just you don't, why 6 vertex? Of course you guess why 6 vertex, because at each single vertex you have 6 ways of doing it. Is 4 choose 2. You have 4 edges, and you have to choose which 2 are out, pointing out, the other ones are determined. At each single locally, you see 6 possibilities, but how they are put together, it's a very complicated combination. Right? Now, if you go to higher dimension, you will have 6 choose 2, which is 15.
For fixed n, if you look at an n by n box in 2 dimensions, is the number known?
You mean the number of possibilities?
Configurations?
Now, this is a classical, beautiful result. So, that's a very good question, but it had been answered 50 years ago. There is a paper by Elliott Leib back in the 60s, maybe early 70s, maybe only 40, I don't exactly know. 60s, 70s, where he determines the entropy. So the great result was, okay, let me answer this question because it's so beautiful. The result was that number of configurations in n times n divided by, logarithm divided by n squared converges, and converges as n goes to infinity, and this is the entropy, which I can't tell you now, but this is one of these exactly solvable models, very beautiful combinatorial and physical ideas. It's done. So this is a very classical, very beautiful paper. But you can make it more complex. Let me not go into the 6 vertex. There is indeed hundreds and hundreds of pages written about the 6 vertex model, and it's still one of the big challenges to be understood. But in particular, this question is done by Leib. Right? Okay.
Another question.
Yeah.
So when you said that let the box size go to infinity, it converges to something.
The distribution converges, yes?
Yeah, but in which space? Because the...
take any fixed size box inside, fixed, so around the origin, take a 100 by 100 size box. but imagine it's embedded into an n by n with periodic boundary conditions.
Oh.
Let n go to infinity, what you see in this 100 by 100, the distribution converges. And what you see in the 200 by 200 will converge, and of course these are consistent. And in this way, in this sense, you have a limit. Yeah? Now, just in all dimensions, so you can go up to higher dimensions. In the second case, so this is the d equals 2. In the d equals 3, we have, in the same paper, we have still super diffusive bounds. I speak about this one. In the d equals 3, we still have expected value of xt squared, but now it will be with the logarithmic corrections will be less than t log t and larger than t log t, and the expectation, the conjecture is that here the truth would be something of this kind. Squared, of course, because I did this. So we are far away from matching upper and lower bounds. Always the upper bounds are almost not trivial, but straightforward. The upper bounds are not, the lower bounds are interesting here because it's about super diffusive. Right. And in dimensions 4 and more, we have central limit theorem with square root of time. So there is a critical dimension. Up to 3 dimensions, it's super diffusive. In 4 and more dimensions, it is, I speak about this example, it is diffusive, I mean square root, the scale by square root of time, and you get central limit. Going to this model, this is when you see the logarithm, that's the critical dimension. So this one from 4 and more dimensions is diffusive. Okay, so these are examples, just I wanted to raise your appetite that these are, I think, not reasonably interesting phenomena. And now let's go to the mathematical formulation and the questions. So I want to speak about random walk in random environment. I have to fix notation. So I fix notation now, and then I put my problem into mathematical terms, right? So I start with a probability space. F is just a sigma algebra on it. I have a measure which I probably denote by pi. This is a probability measure. But not only a probability space, I have a ZD action, translations. So it maps tau Z, mapping omega to omega, with Z is in ZD, and I assume that this altogether is ergodic as a multidimensional dynamical system. It's ergodic. The only events which are invariant, the events invariant under all possible translations are of probability 0 or 1. That's what it is. Just to fix notations, I will denote all along today and tomorrow's talk by this script E, the nearest neighbor possible steps. Just to fix notation, this is dose Z in ZD such that Z is 1. This will be the possible steps of my random walk. I speak about nearest neighbor random walks. I could do it with longer range steps, but don't want to complicate notation. And this is my space of the environment. This is the coin tosses with which the mayor decided how to make the streets one way. Right? I have some.
So this mod Z is the L infinity norm, or
sorry?
This nearest neighbor.
Nearest neighbor.
So is it the L infinity norm or L1?
This is then L1, L
infinity, or
probably it's the same as long as we are on the lattice. No.
No, then.
If you are on the lattice.
So, but
okay,
what
okay.
You are on the lattice. Anyway, nearest neighbor.
Sure.
2D of them. There are 2D of them.
Yes. L infinity the same. Yeah. Sure.
Not L infinity.
I
L
mean,
infinity wouldn't be good.
Yeah.
L infinity is no good. L
No
infinity would allow you to jump to the corners.
Right.
Any anything but L infinity.
Yeah. Coordinates. Coordinates, right.
Anything but L infinity. And I define some jump probabilities. So Pz when Z is in E. So for the nearest neighbors, these are maps from omega to say 0 some, I put some upper bound, S time. I will speak about continuous time, so these are, I will think about these as rates and not as probabilities, so they not necessarily add up to 1, but they are up, bounded from above, right? Such that, you see if I write that? No? So my important constraint here is that, and I write it here, is that sum over Z in E of P sub Z of omega is equal to sum over Z in E of P sub minus Z of tau Z omega. What does it mean? That the sum of the rates jumping outwards, say from the origin, add up to the same value as the sum of the rates jumping inwards from the neighbors to the origin. This is what I call double stochasticity, which is a double stochasticity, right? And now I define my walk. My walk will be xt in zd, but I speak about continuous time. Doesn't make any difference for me. It's more convenient to speak about continuous time than discrete time. As long as the rates are bounded from above, this can be mapped into one another. So it's continuous time discrete. The continuous time random walk is a Markov process. Markov given omega fixed. So once the environment is fixed, then this is a Markovian random walk on ZD, and I tell you the rules. Probability, I put here an omega because that's fixed. Conditional omega, then x d plus dt be equal to x plus e. E is one of these. Maybe better I denote this e. Given xt equals x. I don't write the whole path because I said it's Markov, right? Be equal to p sub e of tau x omega dt plus more order of dt. So it's shifting, then it's exact. So I have a space with a shift, and the jump rates at site x are just the shifted versions of these things, right? So these are random walk in random environment, and x not equals 0. So I start from the origin. This is just for convenience, and just notation. So whenever you see this one omega down there, that means with omega fixed. That I mean is quenched. That's what we call quenched probability. So p omega is quenched probability. And expectation, when you see something like that, that means omega is fixed, condition you average only with respect to the random walk, randomness of the random walk. And when you don't see that, that means integral on omega of p omega of the event d pi omega, and with the expectation the same. This is what, with a bad usage of words in probability, is called an yield. It's better to call it averaged quenched. The quenched averaged out with respect to the. And yield means something different in physics, but I'm not going to. I will use that term, knowing that it's not a very good term. I will still use it. Yeah. And let me make some still notation on these blackboards because I need them. I will need them. I will separate, and let me call this P rather than Z. In a sense, the odd and even part of these guys, as you will see in a moment, I will call S sub E omega be 1/2 of P sub E omega plus P sub minus E tau E omega, and I will call V sub E omega 1/2 P sub E omega minus P sub minus E tau E omega. So this is the average of rate jumping on an edge forward plus backward, and this is the difference of forward jump and backward jump on the same edge, right? And this is useful to have them at hand. I will also have, okay, later maybe, let's note that just by definition, we have VE, okay, of course, I don't write this. This is equal to S minus E tau E omega, and this is equal to minus V minus E tau E omega. So if you think about these functions being defined on edges, then for symmetry, the symmetric part is equal forward and backward, and the anti-symmetric part, which I call V, is anti-symmetric forward or backward. If there are combinatorialists here in the room, they would call these a flow. A flow on a graph means values on the edge, on the oriented edges, which are opposite, in the oppositely oriented edges. Huh? And we clearly have, and mind, before I say we clearly have, flows on graphs for the physicist who is used more with continuous object are vector fields. The flows correspond to vector field in continuum. So the V is a vector field on the graph. And this condition, which is the divergence-free condition, you will easily see that this is the same. This is the same as writing that sum over E of VE omega equals 0. That's exactly the same. And this is a divergence condition of a divergence-free thing. So you have a flow, and that tells you that the flow flowing out from a site is 0. The side flow flowing out. So this is divergence. This is the same as that one. No new thing. So div-free is the same as saying that it's doubly stochastic. Right? So this is my assumption. I make one more assumption before going on. No, before going on, I do the following. I still define some things here. Namely, let me erase that. And let me compute the conditional, the instantaneous drift, locally instantaneous drift. I compute E omega of dxt, condition that xt is in x. So assume that you are at x. What is your speed, local speed? And of course, you easily guess that it's here the rule. You just have to add up the e's, right? So this is sum over the e's. I have e times p sub e, but I divide it into s sub e tau x omega plus sum over e's e times v sub e tau x omega, which is just the same sum over e p sub e, right? Just I separate it. I will call this function some name. I will call, there is a dt, of course. I will call this function, say, psi of tau x omega, and I will call this function phi of tau x omega. These are in RD, because these are vectors, right? So the instantaneous drift is phi plus psi, but I separate it because this is harmless. This is easy. And this will be the important object. Right? This will be the important object. Now let me go on. Let me simplify from now on. I can do it in absolute generality.
What's the intuition for psi? What's the psi meaning?
Psi?
Representing?
Imagine that you are in a random walk. You speak about random walk among random conductances, the self-adjoint random walk. So on each edge you put a conductance, you put a value S. Say, assume V is 0. This is not the case, so in my case it was just the opposite, S was constant, the V was, but assume V is 0 in this formal thing, and that means that on the edges the jump rates on each single edge is the same forward and backward. It's the random conductance problem. So S gives you, this part gives you the random conductance problem, that's a self-adjoint problem, and what I'm looking at is not a self, this makes it non-self-adjoint. This is self-adjoint, this is the random conductance. And what I want you to propose now that, let's assume that from now on that all the S's are 1. Because anyway, they just complicate notation. In my problem, they don't play a role. I can handle them well, they don't play a role. Actually, no, before doing that, I assume, and after that I will simplify, assumption is that S of omega is bounded below a lower star, which is strictly positive. I must assume that this is an ellipticity with somebody, I don't remember with whom I discussed today ellipticity, it was you, right? And this is the ellipticity I need in order to be able to handle the problem. But otherwise, this is just a nuisance for me, notational nuisance, because the important interesting phenomena come from here. So let me make the simplification from now on, that S is simply identically 1. All S's are identically 1. It could be identically something, right? Which is just notational simplification. Okay, then of course this sum is 0. You don't have, if all the symmetric parts are jump, because the minus C and plus C gives exactly the same, right? And this matters, Now further assumptions, this is not an assumption, this is just a simplification. The assumption is this. Good. And I want my walk not to have, yes, before going on, even before making this remark, there is a very important remark to make. The way we look at these problems is the environment as seen by the walker. So you travel with the walk, and I define a process which is the environment seen from the origin. You always are at the origin. The origin is there where you are, right? Which means eta t be tau of xt omega. This is a Markov chain. This is a Markov chain on omega. And since my jump rates, a pure jump Markov chain on omega, since my jump rates are bounded above, there is no difficulty in existence of this Markov chain, and trajectory-wise, good property. So no difficulty with the Markov chain, right? And it is the case, it is true fact, which is easy to check, and I encourage the students to check it, that the bistochasticity, so let me call this condition bistochasticity, which is the same as divergence-freeness, right? That the bistochasticity is equivalent to something what I tell you now. So this is a Markov process, a Markov chain, a continuous time Markov chain. Question?
So don't we have It's a time homogeneous Markov chain, right?
It's a time homogeneous Markov chain. It's time homogeneous Markov chain. But it's in a huge elevated space. It's not in ZD, it's in this space, which is actually an infinite dimensional space because it contains all jump. It's a time homogeneous Markov chain in an infinite dimensional space. Right? Now, this is a Markov chain. At time 0, the distribution is that of pi because omega is chosen by pi. Question is it a stationary time? It's a good question. Is it stationary time or not? And in general, it's not. But bistochasticity is equivalent, actually, to saying that pi is stationary for eta. And not only stationary, but also ergodic. So let's start from this basic fact that I'm not proving it, but the students will have fun to try to prove it themselves. You have to write down the infinitesimal generator or the jumper, take it the discrete time and the transition kernel of this Markov chain and check it, and it's easy to check that exactly this condition, exactly that condition pops up if you want to check. Okay, this is the mathematical reason why bistochasticity is interesting for us. There is a physical reason which I will tell you now because we are here at why bistochastic. The mathematical reason is that we don't have to worry about stationarity. The physical reason is that it corresponds, and I will come back later to this one maybe, but I tell you now just one sentence. This corresponds to drifting of one particle in some incompressible random flow. Incompressibility of the flow corresponds to divergence-freeness of the vector field. Divergence-free vector fields in physics correspond to incompressible flows. So this is incompressible flow, and it corresponds to drifting in incompressible flow with some thermal randomness, and that's why physically the problem is interesting. Right? Okay, so this is a fact that this is stationary. Now I don't want my random walk to have an overall. I don't want my random walk to have an overall speed, ballistic way of going, because that's not my problem. My problem, I want to look at random walks which are not drifting away in that direction with positive overall speed. Nevertheless, I want to understand their limiting behavior. Now x e dxt is, well, it's not e omega. I just erased the e omega. No, it's that. This is e omega with omega fixed, right? But now I want e dxt with averaged out. Now if you look, this is 0 from start because I assume otherwise it would give a 0 in a very simple way. So let me not care about this. It's about is integral on omega of phi omega d pi omega from that formula. So integrate out. This is the quenched. Integrate out. You get and use translation invariance, and you get this one. Now this I want this to be 0.
What were the assumptions of pi?
Pi is just I just said. For example, I gave you
but
3
the system
examples.
is ergodic.
Ergodic. Translation invariant and ergodic. Translations are act in an ergodic way. Right?
So why is it 0?
I assume.
Oh, you assume it's.
I assume. So I want, assume. Yes? But this assumption you will easily see is the same as assuming, and this will be another condition of mine, that integral on omega, v e omega d pi be 0 for all e's. It's the same, check it. You can't have just, okay, that's an easy thing. Let's leave it like that. So this is another condition, let's say no drift. I don't want overall drift, so I assume. Right? Now let's stop for a moment. I have an ergodic, keep in mind this remark, that it's ergodic and stationary and ergodic, but I need space. So from here, from the ergodic theory, if I make these assumptions, and mind that in my examples, these hold. This was by construction of the example was that, and I said that the mayor of Manhattan or the mayor of that city, or in each case I choose coins 1/2, which will ensure this. If in Manhattan you make all streets northbound or all streets eastbound, then of course the driver will have an overall drift going in northeast direction. I don't want that. Good. Now, by the ergodic theorem, it follows already that ext by t almost surely converges to 0. Why? Okay, I run a little bit ahead. Why? Because I write xt like xt minus integral from 0 to t phi eta s ds. Mind, phi is this function. It makes sense to integrate it along the trajectory, right? This is a martingale. Because I just subtracted what I have to subtract locally at each single second. I subtracted the expectation of the next little move. Of course, I add what I subtracted. Right? This is just a tautology, it's nothing. But this is a martingale with stationary and ergodic increments, 0 mean, gives this. And by the ergodic theorem, if it's indeed the case that the expected value of phi is 0, and I integrate it along the trajectory of an ergodic Markov chain which is stationary, yeah, then I get this by the ergodic theorem, right? And if I wrote it down already, then so this is just cheap, nothing, no surprises, so far. I want to understand beyond this. I want to understand the fluctuation. I want to understand. I write here, want either CLT for X or super diffusive bands, depending, of course, on the concrete case. In some cases, I have this. I want to understand when is which, right? By the way, again, a remark. I have to make remarks which I don't prove. It can't be subdiffusive. In this particular case, a simple argument, which I'm not going to show now, maybe tomorrow if I have more time left, shows that it's always at least diffusive. It's easy to prove a diffusive lower bound. For these problems, it's easy to prove a diffusive lower bound. That means that xt departs at least as fast as some positive constant times square root of time, and then that means there is no third possibility of subdiffusive behavior in these cases. Right? Good. Now, how do you want to prove central limit theorem? For the martingale part you have, because we have the martingale central limit theorem for free. We have it. You have to prove central limit theorem for this thing. And that's the difficult part. You have a Markov process, a function on the state space of the Markov process, which is 0 mean. In what cases, under what conditions, does a central limit theorem hold for the integral along the trajectory? So this is the interesting part for this one. For the super diffusive problem, again, this is the interesting part because this is always diffusive. This is always square root of t. It's a martingale. So if it's super diffusive due to the fact that this guy is super diffusive. So this is the part we have to understand. This is the part we have to understand. It's always no use here. It's always good. Now I make another assumption because so far there is one central assumption which discerns, which makes difference between. So far I made the assumption of bistochasticity and of zero drift and the ellipticity. And here is the essential thing, and this has some history. So it goes back to the early 80s or mid 80s. It was conjectured that the so-called H-1 condition H minus 1 condition comes from some Sobolev sort of inequality, which I write down. Namely, remember that this guy, okay, you see it here, that this function is of crucial importance, right? Now let me denote by C sub I and j of x. Okay. Let me look at phi sub I omega, or phi sub I, okay, omega, phi sub j tau x omega d pi. This is it's I and j because these are in Rd. Ij goes from 1 to d. Because these are vectors, d-dimensional vectors, right? This is just a covariance. Call this C sub I j x. It's a covariance. It's the covariance of these translation invariant vectors, right? And call C sub I j hat p its Fourier transform. P sum over x and zd e to the I is now, sorry, this is not the same I, square root of minus 1 of p dot x C sub I jx, where p is in minus pi in the box minus pi to the d. So this is just a Fourier transform. And we know the properties. This is a, okay, let's think about it as a function of p. It could be a distribution in p, but let's think about it as a function. Actually, it's a measure valued. This is a positive definite measure valued matrix. Positive definite measure valued matrix. I mean, measure in p, positive definite as a matrix ij. Now, the h minus 1 condition, the h minus 1 condition is the following. That integral on minus pi to the power d of, let's say, trace of c hat p divided by p squared. P squared is what? Let me write sum over j from 1 to d 1 minus cosine of pj. So this is the lattice Green's function. The lattice Green function, that's important. So this is the inverse of the lattice Laplacian in the Fourier transform of the inverse of the lattice Laplacian. Right? Mind that this behaves like p squared for p small, around 0. Right? Now this integral be finite. This is the h minus 1 condition, which sounds like a technical thing. It's an infrared bound on covariances. It's a bound on the decay of correlations of the drift field. You can't put it in a one-to-one way in X space, because that's why it's formulated in terms of Fourier transform. But you should think about it as a decay of correlation, condition on decay of correlation of these guys. Decay of these correlation, decay with X. For example, there are easy things to say to easy to formulate sufficient conditions in those terms, but it's not easy to formulate it one by one. Assumption is necessary. So this is my last condition. This condition has a history, so it's not me who invented it. It had been around since, as I told you, since the mid-80s.
This cannot be captured through any of the mixing conditions.
Sorry, say again?
This couldn't be captured through any of the mixing conditions?
I don't think this abstract mixing or the alpha mixing. No. This is a quantitative condition, and that one is more qualitative. I doubt that you can write it down in a very clear form in terms of mixing condition. This is, by the way, don't need this general mixing. In some sense, that's too complex, because this is a second order object only. And in some other sense, this this is a subtle condition which in terms of x is different to an exact form. So okay, so let me just say that it had been around for some time. There had been some attempts to prove the central limit theorem assuming this. And what? Okay, now I tell you what my results are. Now I tell you what my results are.
Is the lattice Laplacian coming somewhere in the CIJs?
In a sense, yes, but it's a bit deeper. I tell you, okay. I think in a way I answered your question. Namely, if you look at another process, let's look at another process. Mine. So my point was, I raised it from there, but my point was that I want to understand integral from 0 to t of phi along s omega ds, right? Which means what? That I have this random field, this translation invariant random field. I have my random walk, which is a very complicated, is actually determined by this random field. So these are not independent. And I go along the random walk trajectory and I integrate the field along the random walk trajectory. And what I want to understand, for example, a diffusive upper bound. So I want to understand, for example, expected value of this squared. If this was finite, sorry, not finite, but divided by t. If this was of order t divided by we gave finite in the limit, that would give me a diffusive upper bound at least, right? If I could prove that this is infinite, that would prove the super diffusive lower bound, right? Now let's do a different thing. Let's have y. Okay, I write a similar formula and I tell you what is y. I write a different formula, a very similar formula. Phi tau ys omega ds, where now y is a simple symmetric random walk independent of omega. So you have the random field there, and now you start the simple symmetric random walk and just integrate the field along the trajectory of the simple symmetric. This is what is called random walking random scenery. That's how they call it. It's not a trivial object, but it's a computable object. So I have a random field which has some correlations, and I take a random walk, I let it go along and integrate along the trajectory, right? Now, first of all, what you see here, let me call this some name, let me call it alpha. I put it alpha squared because that's certainly positive. Could be infinite, right? Maybe there is a 1/2, I don't care about 1/2. So let me put here 1 over t and here 1 over t, and let's take here the limit, here the lim sup. I write lim. In this case, it's easy to prove that the limit exists. Again, I don't do it, but it's easy by some monotonicity to prove that the limit of this guy exists as t goes to infinity. This is a self-adjoint problem. That's not a self-adjoint. For this one, I can't prove that the limit exists directly, but I can prove the lim sup certainly exists, right? Now, this alpha squared is actually equal to this. That's a computation, again, very good for the students to do, that if you want to compute, you arrive exactly at this thing. So that alpha squared. And something what is not straightforward to see, but in this business I'm speaking about, is known, nothing new, it's known, but it's far from trivial, is a bound like this. So if you integrate it along the trajectory of an independent random walk, you get something bigger. Not so. maybe there is, I don't care now about factors, maybe there is a factor 8 or something like that, but there is a factor, there is a which are easy to prove there in our papers, but we took it from other sources, so this is what has been done. So let me go back to the logic. If this holds by straightforward computation, not good exercise computations, this is equal to that. I mean, if this holds, then this is finite. And from other arguments I know that this is bounded above from there. So if this holds, then at least I have a diffusive upper bound. Right? Now this is my condition. Under this condition, I know already that there is a diffusive upper bound. The question is, okay, you have a diffusive upper bound, do you have the central limit theorem? And that's a subtle question.
Yeah, just one simple thing. Actually, this condition, the H minus 1 conditions, yeah, that only basically giving the condition near 0.
Yeah.
And near 0 is known to be the depending on long range dependence.
Sure.
That's exactly
Perfectly
the
fine.
case.
Yeah. So that's the long range. That catches in a way the long range correlations.
Long range correlation. Yeah.
Catches the long range correlations. Exactly what it is. No, only 0. Yes, I didn't emphasize. Higher, I didn't say explicitly.
Yeah.
But only that.
Only near 0.
Only
yeah.
this matters. Nothing else.
Exactly.
Nothing else matters. Right. Now, and I'm ready to formulate the theorems. There are two things I'm stating. One is stronger than the other one, so in the end, but these are two papers which came out in very short time, one after the other one, and both contain important things, I think, in my opinion. Good? Good. Give me a second. So theorem 1. This is joint with Gadi-Kozma, and it's in the annals of probability just out in December. It wasn't submitted much earlier, it took some time till it went through because it happens these days that. Assume what's said. Assume divergence-free, which is the same as doubly stochastic, plus, okay, by the way, I assume that there is no drift, that integral of V is 0. But now, if we introduce all these Fourier transforms, correlations, and so on, if that integral of V was not 0, then this measure C of P, which is a measure, would have a delta at P equals 0. So actually the H minus 1 includes the no drift. No drift follows from H minus 1. So I don't say explicitly, no drift follows from H minus 1. So ellipticity, I write here ellipticity because for the symmetric part there was ellipticity. Plus H minus 1, right? Then it is true that, let me see how I wrote it here, then xt by square root of t converges in distribution to a non-degenerate I have to tell you what's said. So this is convergence in distribution, but what probability space? Question?
Infinite dimension?
Yeah, so it could be all finite. I give you only the one-dimensional marginals, but all finite-dimensional marginals. We don't have the tightness. We didn't do the tightness. It could be done, but we didn't do it. So without tightness, all finite-dimensional distributions. Now this is difficult to, okay, more than annealed, but less than, halfway between annealed and quenched. Let me say halfway. Tomorrow I will have times for technicalities, so maybe I have time. So this is between annealed and quenched. Let me put here by 2. Quenched is stronger than annealed. We don't have the annealed. We don't have the quenched. we have something more than the annealed, and let me not go into. So if you want, then take it for as annealed. So with respect to the averaged problem space, but it's more than, right? So this will be. I have to tell you that this type of theorems. Okay, first of all, there is a famous survey paper of S.M. Kozlov back in 1985, where he claims this theorem, but the proof is not complete. There is some very important thing missing there, and that's why other people still started to work on that, and it was. And there is a paper of Komorowski, Tomasz Komorowski, and Stefan Olla back in 2003, where they claim to correct the error in Kozlov's, but they make the same error. And they realized that later. and there is the book of so what I claim is that what I say is that they claimed the result, but was not complete the proof. Claimed the result, but was not complete the proof. There is the book of Komorowski and Landin and Stefan Olla in 2012. This is this huge Springer Grundlehre der mathematischen Wissenschaften about fluctuations of Markov processes, and they have a chapter about this problem, and in that chapter they say that this proof was incomplete. Actually, they missed the same thing as they just did. And they give a proof for weaker, under stronger, much more restrictive conditions, which I'm not going to tell you. But they give a proof under more restrictive condition. Maybe later I will have time to tell you. So this is the final result, and Tomasz Komorowski was the Stefan Olla was the associate editor at the Annals of Probability, and Tomasz Komorowski, I know from later I learned, of course. And Komorowski was the referee, so it's referee. So that's the result. Okay, I will tell you the proof tomorrow. I mean the main points of the proof tomorrow. Now, in order to go to the other theorem, which will be the quenched version, I have to state a number of things before, which are interesting and important on their own. There is Helmholtz's theorems. This is 19th century mathematics. Which you all learned, those of you who did some physics, did some electrodynamics, learned. Namely that Helmholtz's theorem says the following: let V be a vector field. Okay, it's an R3 because people in the 19th century were interested in R3 and electrodynamics in 3 dimensions only. R3 and R3, which is smooth and divergence-free. No randomness. Right? I don't give you full conditions, but so there is a divergence-free vector field on R3. So what Helmholtz says is that there exists another vector field H on R3. This is what in electrodynamics we call vector potential, such that V is the curl of H, or rotation of H. Everybody knows what rotation is, yeah? Should I explain what the terms? Should I explain the terms? Yes? Okay, this means the following, that V1 is equal to D2H3 minus D3H2, and go on by circular permutation. Good? So that divergence-free vector fields are curls or rotations of vector potentials. There are other, so okay, that was in 3 dimensions. In 2 dimensions it's actually simpler. in R, if V is in R2 to R2, and divergence of V is, by the way, I didn't explain divergence. Should I say what the divergence is? Everybody knows?
Maybe we just wait.
Sorry?
So there are some students, so maybe.
Okay, so divergence means that some I goes from 1 to D, or let's say in any dimension, D is di of Vi. That's the simplest way, the most direct way. So the sum of the directional derivatives in the three orthogonal directions. This definition relies on how you, but there is a frame-free formulation, just it takes more time. Good. Now, if V is in 2 dimensions, then this object will not be, so it's not the case that vector fields and vector fields is dimension dependent. If you are in 2 dimensions, then H will be R2 to R, such that V1 is probably D2 of H, and V2 is minus D1 of H, if I'm not mistaken. Which means the same. Let me not go into vector analysis now. So this is simple. This is the 2-dimensional rotation. I say this because many of you have heard about height functions nowadays. This 2-dimensional statistical physics is so much done, and the height functions always pay. Now this is exactly, the height functions come in through help, where people don't speak about this because probably they don't know.
Is this H unique?
No. In 2 dimensions, yes.
Oh, in 2 dimensions?
In 2 dimensions, except adding a constant. In 2 dimensions, up to adding a constant is unique. In 3 dimensions and higher, by the way, in higher dimension, it would be some tensorial objects.
You can subtract some kind of gauge to
exactly.
all the time.
So there is a free gauge to be chosen, which is very important, and it will have a role later in mind. In 2 dimensions, you can add only a constant. In 3 and more dimensions, there is a gauge, and the gauge that means that there is a non-uniqueness. You can have some choice. And there is something what is called the Coulomb gauge, probably I've heard about it, and the Coulomb gauge is the canonical choice, and in many problems, and in my problem, the Coulomb gauge will be the canonical. Now these things make sense on the lattice too. Let me not go, maybe tomorrow I'll postpone every technical things for the tomorrow talk, but this can be done on the lattice. So as, of course, no surprise, so ZD is an approximation of RD and many things, and differential calculus and so on. Just you have to be, it's a bit more combinatorial, the symmetries are a bit different, and you have to be very careful. But trust me that if V is Z3, okay, if V is a flow, if V is a divergence-free flow corresponds is divergence-free flow in R in ZD. That means V on each lattice edge, oriented lattice edge, takes a value, and the value taken on the opposite oriented edge is negative of the forward. And the divergence free means that around each single side, if you add the outgoing flows is 0. Right? That's what we call flow, and divergence free is what it is. Sourceless flow. Sourceless flow on ZD. That corresponds to. Then there is something, an H, a stream tensor, let me H, a stream tensor on Z, this was in Z. Okay, I can, okay, let's take Z3. Yeah, okay. And this is on Z3. Let me put here somewhere a star, because on the lattice you have to shift by 1/2. There is a dual lattice which is shifted. Let me now go into very much deeply into the details. But there is an analog object like helmholtz, a discrete object like helmholtz. those interested will find details. Okay, now, and my V, the V was like that. So mine, if I define Vx omega be just V of tau x omega, the shifted, right? That's exactly this type of object. So due to Helmholtz's theorem, I know the following. I know the following. This V is the translation of, so this is stationary. This is a random field, a random flow on the lattice, which is stationary and ergodic. It arises as the lattice version of the curl. It is lattice curl, so V is lattice, it makes sense, curl of H, which I'm not telling you what it is, but you can easily guess actually if you sit down and you want to guess. So it's the lattice curl of H. The curl is a differential, is a derivative. This will be a sort of lattice derivative. Now if this guy was stationary, and it's a derivative of a random, this by force it's random. And as you said, it's not unique, but I choose the Coulomb gauge. Right? Now, then H will not be stationary necessarily, it will have stationary increments because its derivative is stationary. So H, which is this stream tensor, is stationary increments. So that means that if you take the increments, those have stationary distribution. Take a value here, take a value there, and shift it this way. Right. Good. Now it turns out that the H minus 1, by the way, this H is not that H. When you write this H is script. This is from Helmholtz, this is from Hilbert. The H minus 1 condition, the previous H minus 1 condition, is equivalent to saying, that's a condition, that H is actually stationary. That means that H at x and omega, mind this H is not a number, it's a more complicated thing. It's a sort of tensor, but I just schematically. But it depends on site and randomness. It's stationary increments a priori from Helmholtz. But what I know, what the H minus 1 condition is, that this is actually H tau x omega. So it's a stationary field. And where with H in L2. So the H minus 1 condition is equivalent. This is just an equivalence. If there in that paper you find a chapter where this is put. It's not a very, once you know what you need, it's not terribly difficult. That the H minus 1 condition is equivalent to saying that this object which is a priori stationary increments is more restrictive, it's stationary, not only stationary, square integral. Right? Now going back, there was, I said that Komorowski and Molla have a proof. Instead of this square integrability, what they need here is in 2 dimensions L2 plus epsilon, and in more than 2 dimensions LD, which is a much more restrictive thing. And the proof is totally different of ours is better. Good. Now, in order to state the quenched result, I make a slightly more restrictive. I make a slightly more restrictive. I say, let's say H minus 1 plus epsilon condition. You will see why. All those things hold, but I assume that the H you get here is not just L2 but L2, slightly more integral. H is L2 plus epsilon. in all in any dimensions. Epsilon doesn't depend on the dimension. A little bit more than to interpolate I need for the next result. Right? So I said everything holds, so at h minus 1 condition, you remember what I said is equivalent to this one, but here in the end I assume a little bit more. Now under these, theorem 2 is myself only, and it's annals of probability accepted, probably this year I hope it will be published, plus, because it's not quite guaranteed. Assume divergence-free plus ellipticity plus h minus 1 plus epsilon together, then xt by square root of t converged in a quenched way, so let me put here p omega with omega fixed to for pi almost all omega. So this is the quenched result. Of course, the quenched result is stronger from the if I have this holding for almost all omegas and this sigma is deterministic, is not random, then of course the right? So these are the two results, and I stated both because in order to prove that, I need some technical parts from this proof anyway. I wanted to mention Gadi's name because the first paper was written with Gadi, and that's a more, I have absolutely no idea what it's.
Yeah, so if you can,
I'm over time now.
that's okay.
Somewhat over time. Good. So then I stop now. I think I gave the results, and tomorrow I continue from here. So tomorrow I will give you some of the technicalities, which will include technicalities from here. Not only that. So when I say technicalities, don't think that boring technicalities. I don't want the interesting technicalities. So the proofs, ideas of the proofs. Let me just give you 2 more minutes only. There will be functional analysis. And I know many of you want functional analysis, or at least I know it's strong. Functional analysis is strong here. So, down to earth, that means concrete operators, spectral analysis, and resolvent calculus, and so on, concrete operators. There will be some ergodic theory part, which is softer but fun. And there will be an extension of the famous Nash moment bounds, which I will tell you what the Nash moments bound are very important things dating back to the late 50s by John Nash. And there will be non-trivial extensions. And all the point is, let me emphasize once more, and then I finish indeed, that all what I do is non-self-adjoint. So that's why the novelties always come from the non-self-adjoint, not reversible non-self-adjoint. Thank you very much. I'm open to questions.
Questions? We have quite a few in the middle of the lectures. Then you can also ask tomorrow.
Yeah, just one quick question. So actually, when the dimension increases, that means your variability decreases in some sense. That's what you were saying.
Yeah. So that means that the diffuse it's less super
less
diffusive.
Variable.
Yeah.
Less variable.
Well,
overall
but it will
variable.
stay diffusive, so it's not going down to 0.
No. Yeah.
But a super diffusive behavior is expected and happens in low dimensions. Of course, because you have this 1 over p squared, as you said, and if you go to higher dimensions, that's more and more integral, right?
Yeah.
So 3 is in general. There were other models where 4 was the critical dimension, but it had some special reason for that. But 3 is the dimension when things change. Typically, that's because of the integrability of 1 over p squared.
Okay, any more questions? Just thank Bálint and tomorrow, please.